Okay, we have two structured questions to go through. The first one is on titration. If you haven't reviewed the question, I want you to read through the question very quickly. And if you need to, you can pause the video down. Okay, I hope you have read the question. I'm going to go through roughly what the experiment is about through this scheme over here. We have over here 7.84 grams of iron salt. Okay, you place it in 250 cm cube of water and you get a 250 cm cube of iron salt solution. You draw out 50 cm cube of the iron solution and you put it in a burette. Okay, on the other side of the experiment, you have a conical flask over here and you place 25 cm cube of KMnO4 together with 10 cm cube of sulfuric acid. Next, you are going to do a titration of the KMnO4 with the solution in the burette. So what you can observe is that the conical flask is filled with purple KMnO4 and that the burette is filled with light green Fe2 plus solution. So the KMnO4 is going to turn from purple over here, the purple, into a colorless solution, and you are going to see the Fe2 plus solution from the burette turn into a yellow solution of some sort inside the conical flask. The oxidizing agent in this case is MnO4 minus. Okay, this is the oxidizing agent, and the Fe2 plus is the reducing agent. So the first question calls for the filling up of the titration table. So make sure that you have 2 dp for all your readings. Okay, quite an easy question. I think most of you got it correct. The next part is slightly more challenging for some of you who are not so aware of the average volume of solution used. Now you can see that we did 3 titrations here, but only 2 of them are consistent. Yeah, this one and this one is consistent. Other than that, the others are this one is not consistent. So when it comes to determining the average volume of solution used for titration, we will not use the 26.80 cm cube for calculation. So you can see here, we only use 26.60 and 26.50 for calculation for the average volume. And you get a volume of 26.55. Okay, in part 2 of the question, you are asked to suggest why no indicator was used for the titration. So there are 3 things you should tell me. The first 2 things over here, okay, the first 2 things you should tell me are the color changes for the 2 chemicals. You should be able to tell me that the iron 2 is originally light green and it will turn to yellow after the reaction, and that for the potassium manganate originally is intense purple and after the reaction is colorless. So even after writing down these 2 color changes for me, you still got to conclude your answer by saying that the reaction is self-indicating or that the reaction color change is very obvious. Because by just telling me the color change, it is not obvious that you understand this point. So tell me that originally the conical flask is purple in color because we have KMnO4 inside there, and then it's going to turn to colorless. So you can either say it's colorless because if the concentration of Fe3 plus is very low towards the end point, you won't be able to see the yellow color. Alternatively, if you have a rather high concentration of Fe3 plus, you should be able to see a pretty intense yellow color in the conical flask. Now some of you might say that why not we use 1 excess drop of Fe2 plus from the burette. which is perfectly fine. The color change would be like green, yellow, but in this case, I'm not really looking out for a very precise color change. You just have to show me that you know roughly what the color change is, and I'll give you the mark. So over here, the word yellow is alright. If you say it's yellow green or green, I will still give you the marks. Okay, for the third part of this question, is really a giveaway. All you have to do is to consider the molar mass of the elements inside this formula, and you do a very careful calculation of the molar mass of this hydrated ammonium iron 2 sulfate with working. One thing that some of you are very careless about is the decimal place. Remember, I told you inside in calculations, mole calculation, that molar mass you always have to write it to 1 dp. Yeah, so even though it is a 0, you got to tell me it's 392.0. Okay, you can't write just write 392. Okay, so the 1 dp on the molar mass is very important. Okay, so for part 4 to part 6 of the question is really the more difficult mole calculations. So in part 4, we are asked to determine the concentration of ammonium iron 2 sulfate solution prepared. So if you can remember the scheme which I showed you just now, over here, let me just scroll it up a bit more. Okay, over here. Now you see that we have 7.84 grams of iron salt, and we put it in 250 cm3 of water. So to determine the concentration of the iron salt solution is actually pretty easy. We have to divide. Let me just scroll it up a bit more. We got to divide the mass of salt used by its molar mass first. Yeah, so this is from the previous question. When we determine the number of moles of ammonium salt used, we can then determine the concentration of the salt solution. Because this is the number of moles, we put it in 250 cm3 of water, so we get a concentration of 0.0800. And from the second part of the question, in which we were asked to determine the average volume, we calculated a volume of 26.55. This value is different from the 0.0800 because I didn't round off this value. I took it from the calculator directly. So I have a concentration multiplied by the volume in dm cube. It will give me the number of moles of the salt used. There might be some question about how come the number of moles of Fe2 plus is the same as the number of moles of the salt solution. And that is a very valid question, because if you look at the formula of the salt here, okay, the formula of the salt here, you can see that in one whole formula of the salt, I only have one ion of Fe. So in actual fact, the salt is to Fe2 plus ratio is 1:1. Yeah, so therefore, whatever number of moles of salt are used will be equivalent to the number of moles of Fe2 plus that has reacted. Okay, in part 5 of the part 5, okay, the number of moles of MnO4 minus reacted was 1.06 times 10 to the power minus 5. You are asked to calculate the concentration of the KMnO4. So very straightforward calculation. We have the number of moles. This is in terms of moles. This is in terms of volume. So number of moles over volume will give you the concentration directly. There is a change in the marks here. Yeah, so very, very easy question. There is an error in setting question number 6, so that's why I cancel it out for all of you. Okay. Basically, if you do the actual calculation, you will find that the value of x and y from the perspective of mole ratio is just impossible in this reaction. So there was an error in setting up the problem, and I've got to apologize for that. Okay, so there is the end for structured question number 1.